Good morning. My name is Misha Buzinier, and I'm a software architect for life sciences products and solutions in HealthShare Group. And today, together with my colleagues, we would like to talk about text analytics and natural language processing in computer world. Let me introduce Misha Tsatsulin, who works together with me on this topic as a software developer and as analyst. We're still missing my second co-presenter, Dirk van Hyfte, who is a co-founder of iknow, the inventor of technology, and I hope he will join us in a few minutes. But meanwhile, I will start the presentation. As I said, I want to discuss how it's possible to get some value out of free text using a computer. And I will start with some theory describing different approaches. Then I will talk a little bit about our own offering, the product called iknow, or the technology called iknow. And I'm really have a passion about this technology. I think it's a great technology. So if you notice a shameless marketing pitch in my presentation when I talk about iknow, I hope you will forgive me. Then I will move to practical applications and talk a little bit at how those theoretical concepts that we discussed in the first part of the presentation can be applied to a few practical use cases. So let's start with theory and with conventional approaches. First of all, I have to say that text consists of signs. Those signs can be different, but usually in text they're just alphabet. Those signs form syntactic structure. And when we try to extract some value out of the text, we basically have two possibilities. We can try to analyze this syntactic structure and get the value out of it. Or we can try first to map this into some semantic meaning and then apply some rules to those semantic meaning. Well, there are some tasks that really can be done on syntactic structure. For example, one can distinguish between Russian and English text without understanding what is written. Just different letters are used. Or one can estimate a richness of a student vocabulary just by counting unique, distinct words used in the essay without also understanding what is written in this essay. However, of course, more complex tasks would require applying some semantics to the text. And from mathematical point of view, that means a mapping from syntactic space to semantic space. And there's a problem with semantic space. Again, mathematically speaking, the problem is that it's T1 separable. I'm not sure if anybody understands what that means here, but basically that means that on intuitive level, it's sometimes very difficult to distinguish one meaning from another meaning and separate one from another. I would say that research into semantic spaces was quite popular about 30 years ago when I started my career. And then the hope was that it would be possible to create programs that debug themselves, for example. As most of you know, that didn't really come to fruition now, and that shows the complexity of the whole idea. But still, first, let's discuss how we can extract value of the text using syntactic structures. The most popular model to work with syntactic structures is bag of words model. This model is based on basically very simple mathematical concept of vector space model. I'm sure that everybody studied it in high school and maybe in college. It's easy to deal with it with 2- or 3-dimensional spaces. Unfortunately, texts will not be 2 or 3 dimensional spaces, as each word, each unique word will form a dimension, and large corpus of data can contain hundreds of thousands and millions of unique words. So we are working in a space that has millions dimensions. To perform most of the tasks in this space, we will need to reduce this dimensionality in some sense. And this will require more elaborate mathematical techniques like principal component analysis or single value decomposition. This approach actually works quite well for document retrieval. And you know everybody uses Google. You just type a few keywords and you get a result. And that's basically relatively easy. So I'm oversimplifying things. I hope that's understood. Google does some smart things, but the basic idea is that it reduces the dimension to the number of keywords you typed and just searches in this subspace. More advanced tasks like document classification or personalization of the content delivered to you by the internet, like spam filtering, really requires SVD or PCA. There was some research works into really even more advanced applications like question answering and essay grading, but the essay grading is based on similarity of the essay to a set of reference essays. So if somebody would write a really original essay, that would be missed and probably get a low mark. And by the way, machine translation also uses this simplified approach. When you try to translate something on Google Translate, it doesn't try to understand what you have typed. It's just searches for similar sentences in the past history and returns the best results of the translation. There are some extensions of the bag of words model, and mostly they're based on works of a famous philosopher of early 20th century, Ludwig Wittgenstein. And those extensions basically fall into 2 categories. The first is that we replace a term document matrix with word context matrix. So we try to look at words in a specific context. And the second extension, we replace the term document matrix with pair pattern matrix. And I will talk a little bit more about it when I will come to iknow, because iknow evolves on this approach. Well, these techniques really can be used for more advanced things like automatic thesaurus generation or named entity recognition. Well, if we really want to start with semantics, then the most popular approach is called merge. And this approach was proposed by Noam Chomsky, who is, I think, a famous and very controversial figure. And the idea here is that syntactic elements can be merged into higher level syntactic elements that can be used in the same way in a sentence as the lower level. For example, on the sentence here, John went to movies, and John and Jane went to the movies basically play the same role. So this kind of recursive approach that allows to merge concepts, and by doing so, it gives you some semantics on the structure. The merge approach uses what is called constituency grammar, which is based on bottom-up structure of the sentence. One downside of it that it ignores another flavor of grammar that is called dependency grammar. Merge addresses some of the limitations of the bag of words model. For example, consider those 2 sentences written on the screen. They have exactly the same bag of words. Words here are the same, but they have different meaning. So bag of words model is not able to distinguish between 2 sentences. The merge approach gives you a constituency parse tree, and you can see here, well, you probably cannot see, but here we see 2 families, and here we see 10 cars, and here is the opposite. So by looking and working on this graph, it's possible to distinguish and understand those sentences. One downside of this approach is really that it's difficult to handle sublanguages in it. Merge requires a really full linguistic model for a language. Sublanguages is something that is used in specific domain. For us, the most important domain are domain of clinical notes or pathology reports that is used by clinicians. The notion of sublanguage was introduced by linguist Zelig Harris in 1988. And look at this sentence that is taken from a real note. You can understand it, but as you can see, Merge doesn't understand it. It thinks that this BID, TID is a verb here. So because, well, if you say like ensure bit T test tolerated, you might mistake it for a word if you don't know what it means. If we compare back-of-words approach to Merge, I must say that the main advantage of back-of-words that it is based on very simple mathematical model. Things like similarity or correspondence of the query to a document described by easy mathematical concepts like distance, cosine between two vectors, and so on. Therefore, behavior of these models is relatively easy to understand. It's simple to debug and tune. Well, nothing is really easy, but at least you understand what you are doing. However, it is limited because, as we said, it completely ignores grammar, as in an example 2 slides before. And also, it ignores the fact that words can have different meaning. And we will review an example of this further. Extensions of back-of-words models do address those limitations, but then we'll lose the main advantage, the simplicity of mathematical model. Well, if we look on the Merge, I intentionally put this background to illustrate that it's really difficult to understand what Merge is. It's almost as difficult as to read, on, at least on my screen, what is written on this slide. It's based on a well-defined but very complex set of mathematical models based on graph theory. And there's not even a consensus of which model is the best here. It requires extensive mathematical model for each language, And as far as I know, the only complete model exists only for English. There are some models for other languages, especially popular languages like Chinese, French, German, but they are incomplete. And as we have seen, it doesn't really well handle sublanguages. Finally, it's really extremely demanding for computational resources. Implementation of classical approaches, well, back-of-words is traditionally said is implemented by Lucene and Solr. And the Merge is implemented by such APIs as Stanford Core NLP and Apache OpenNLP. I must say that both of those implementation also include some dependency grammar and extensions of back-of-words model. So they implement a little bit more than just Merge.
Okay. So let us talk about how these implementations are used in practice. So the widespread approach is to use a framework for, for the analysis of text. And then the main architectural principle of such frameworks is to split a complex task into a series of simpler tasks, simpler pluggable tasks. That allows for code reuse and for simpler general flow. So there are 2 major general frameworks. It's GATE and WIMA. GATE stands for General Architecture for Text Engineering and was developed by University of Sheffield. WIMA stands for Unstructured Information Management Architecture, was developed by IBM, and now they are both open source. They provide interoperability between each other, so each one can call other in a wrapper. UEMA is defined more generically. It's not only for text, but for any unstructured data, for video, for audio. And UEMA has created is completely empty. It's just manages how components should interact with each other. And it's current industry standard. It's not a surprise that IBM Watson uses UEMA for unstructured data analysis. And let's look again at the example of components. So as we mentioned, Solr and Lucene, they're integrated with UEMA as well as OpenNLP. The simpler analysis engines like samples would be simple annotators like snowball is a stemmer, regex annotator, idle time is a temporal tagger, diction annotator which finds entries from a dictionary. It's also worth mentioning UEMA Ruta. It's a rule language which works with annotations and might update or create new annotations. And as yet another it's worth mentioning to like Apache Syntax. It's a clinical text analysis and knowledge extraction system. It's an UEMA component which allows to find medications, symptoms, co-references, etc. UEMA has built-in scalability extensions, asynchronous scale-out UEMS, which is based on queues, and real-time distributed cluster computing. And InterSystems is packaging iknow as a pluggable component, so it is possible to combine it with the rest of UEMA components.
And now we will talk a little bit about iknow. In my opinion, iknow gives you the best of both worlds. iknow is also based on vector space model, only the dimension in this space is not a single word that doesn't have the real semantic meaning, but a semantically meaningful word group that is identified by iknow. So each dimension, each single dimension already has some semantic meaning in this vector space. It's also based on a bottom-up approach to a sentence as merge, but instead of constituency grammar, it uses dependency grammar. And it also evolves the idea of pair pattern matrix and introduces the concept relation concept patterns. Please do not mix concept relation concept with a subject predicate object triple. These are very different, and we will talk about it a little bit later. So here is an example of how iknow works. So for this sentence, it first splits it into two concepts and one relation, and then creates an index on it. And here you can compare the constituency graph and dependency-based graph provided by Stanford NLP. You can see that dependency graph is basically very close to what iknow provides here.
Okay, so now that notions of concepts and relations were introduced, let's elaborate a little bit further on UEMA integration with iknow. So concepts and relations and negations could be presented in UEMA as annotations. So let us go to the next slide. So that shows UEMA annotations in Ruta viewer, and here we can see iknow concept annotations, iknow negation attributes, as well as third-party annotations. For example, temporal markers from idle time, and simple dictionary matches from dictionary annotator.
Okay, let's a little bit talk about how iknow compares to bag of words. As I said, iknow is different in the sense that a vector in vector space has a semantic meaning. Here's an example of dopamine. The word dopamine can mean many different things, though it's the same word. It's not really an homonym, but in different settings, it has different semantic meaning as this illustrated here. However, from the bag of words point of view, all those 5 phrases are not that different. If you represent them as a vectors, those vectors will have a small angle between them, and so they will have high similarity. When we compare iknow to merge, one thing that I should highlight and emphasize is that iknow works much better with sublanguages. Again, this is an example that I gave about ensure BID TID as tolerated. If you remember, merge didn't handle it, while iknow actually provides relatively good representation for it. So to summarize how iknow compares to conventional approaches, the first thing I should say that unfortunately, at least at this moment, we do not have a really good and well-defined mathematical model for iknow. That leads again to some difficulties in debugging applications based on iknow. And one of the problems here that it's really difficult to distinguish when technology behaves correct but gives you counterintuitive results, and when it is an error, a bug in your application or in our engine. So that creates some headache. Another common misunderstanding, as I mentioned, is that CRCs are not really triples. Computationally, iknow is not resource demanding at all. It requires much less resources than SVD or PCA used by bag of words, and certainly much less resources than full parsing used by tools like Stanford NLPs. It supports multiple languages, but of course, it still requires a linguistic model for a language, so we cannot support all the languages, but I guess we support about a dozen now, right? 10, okay. And as I have shown, it can be easily tuned for sublanguages. And in addition, iknow includes some built-in dictionary matching, both to user dictionaries and to standard ontologies like UMLS. And finally, it actually defines 2 vector spaces that can be used in conjunction. Beside a vector space based on concepts, it also provides a vector space based on concept relation concept patterns. So now I will switch to some practical use cases, and I will review 3 use cases, and we'll see how all those 3 techniques work on those use cases. First will be a document retrieval by query, basically what you do when you do a search. The second will be information retrieval from just one sentence, something that Siri does when you speak into your iPhone mic. And the last one will be information retrieval from a large corpus of text. For example, identification of patients that are of high risk of something, of stroke, or of care mismanagement, or something else. And if we look at the document retrieval, well, Solr works pretty well. You probably don't need anything else if the only thing you need to do is to retrieve document by query, and the query is well defined. It's a very different situation if you don't know the query. If you look for something, but you don't quite know what you're looking for. But when you know the query, it just works. Well, Stanford NLP is another tool that I compare. It just doesn't help you. It's not intended for use for retrieval of the documents by a query. iknow has some, it's a mixed case. It has some advantages and disadvantages. The situation here is that with iknow, normally you will need to do a 2-step search. First, you search for entities based on your query, on a number of words, keywords in a query, and then you search for documents that include those sentences. This is very fast because of this 2-step approach. And it really works faster than Solr would do. But on the other hand, it might miss some of the results. For example, if a query is those keywords are split between several different entities, you might miss those results. And also, I must say that I know indices require a lot of space compared with indices used by Lucene. We cannot avoid this. But we have another product in our stack called iFind that is probably a proper product for this kind of use case. If we look at the understanding a sentence, let's look at this sentence. Patient being under care of his wife suffered a severe paralytic stroke on Monday. Lucene and Solr, well, they can help you, but only if there is already a corpus of data where they can look for something similar, and then there is ready responses, some semantic analysis of this, they can provide, retrieve you this semantic analysis. With absence of the corpus of data, they just of no help at all. If we look at the Stanford NLP using constituency grammar, it actually provides quite good understanding. It tells you that patient is being under care of his wife. It tells you that patient has suffered a stroke, and a stroke was a severe paralytic stroke. From this graph, it's easy to create a program that will give you all this information. If we use Stanford NLP, but with dependency grammar, it becomes much less clear. For example, patient and a wife are siblings in this tree. So it's not clear at all who has suffered a stroke, a patient or a wife. Well, iknow is based mostly on dependency grammar, so it's not surprising that just looking at iknow results, you might have the same confusion here. We have a CRC that says wife suffered severe paralytic stroke, and this is an example. This is a correct CRC. This is a concept relation concept pattern. It's just not a triple. You cannot interpret it as a triple. So again, this is a correct but counterintuitive result of the technology. Well, anyway, at least it gives something compared to Lucene. The third use case that I want to discuss is information retrieval from large corpus of text or text classification. They share a lot in common. And one thing that they share in common is that up to 95% of the effort you need goes into data preparation and manipulation. You need to extract data from appropriate sources like clinical systems. You need to clean it up. You need to featureize it, convert to something to which you can apply a model. This makes doing proof of concepts on this kind of projects very difficult because, well, you need to invest upfront almost the full future cost of the project just to understand whether it will work at all. Well, both tasks require some inference, some reasoning. And that means that we really need some rules. Whether those rules are written in some rule definition language or whether they're just using some machine learning classifier doesn't matter, but we need rules. And that means that we need to first map the data into semantic space. We cannot work on syntactic structures to do complex inference. So that's the first thing that we need to do. And a bag of words is semantically agnostic. Users can define some semantic mapping on those bag of words. But even if users define it, it will be difficult because semantic meaning will be associated not with a single dimension, but with multiple dimensions, which means that we're talking not about just dimension, but subspaces or hyperplanes. It's a little bit more complex mathematical objects. NLP tools actually helps you with semantic mapping. Maybe they do not give you it out of the box completely, but since they can identify triples like subject, predicate, object, it is much easier to do. IKnow includes some latent semantics because it determines semantic boundaries for meaningful word groups. And thus, again, we work in the vector space where each dimension has a semantic meaning. But in addition to this, it also excludes meaningless morphemes like determiners, pronouns, and so on. It splits concepts and relations. And finally, by giving you discrete concepts, multi-word concepts, it simplifies the task of mapping this to some ontology that can have a very rich semantic content in it, like SNOW-MED-CT, for example. Typical use cases where one would need this kind of inference is to identify patients with sepsis in the emergency department notes. And as far as I know, InterSystems had a very successful proof of concept on the west coast of the United States, applying our technology to this. It also can be used to recruit patients for clinical trials, or, for example, identify patients with a high risk of stroke. And I will talk a little bit more in details about this use case. And as an example, I will look at a data set provided by I2B2 for some linguistic research, specifically for so-called smoking challenge. That's an open source data set that anybody can download. And it consists of 500 clinical notes, about 200,000 words. An average document has a length of 350 words. We found 17,000 unique words there, while IKnow identified 40,000 unique entities and 50,000 CRCs. And NLP found 75,000 unique noun phrases. So first thing that we need to do, as I said, is to reduce this dimensionality. You might suspect that as initial dimensionality of IKnow is somewhere between the number of words and the number of noun phrases. IKnow will behave somewhere in the middle between those two techniques. And here I show you the coverage profile. So what is on this picture? The horizontal axis is the number of objects you need to use. So those objects are monograms, single words in case of words, the noun phrases in case of application of NLP merge approach, and the IKnow entities in case of IKnow. So the number of words you need to successfully classify a percentage of documents in the corpus in those 500 documents. And as you see, with words, theoretically, we could cover about 80% of the corpus. With IKnow, we only go up to 60%, but with NLP, we cannot even reach 60% if we go to thousands of noun phrases. But we shouldn't forget that when we work with single words, again, if this classification is on something simple, that will work. If it requires semantic meaning, those words do not have semantic meaning, so it's actually much more difficult. And on the other hand, if we will use IKnow with semantic meaning, specifically when we map IKnow concepts to UMLS, we get almost 100% coverage on this, and this coverage is achieved much faster than if you would use tools like Stanford NLP that provides you with noun phrases. So I would say that IKnow performs better than either bag of words or merge models for information retrieval from a large corpus of data. Here's a workflow example that we used in for identification of patients with high risk of stroke. So we took some coded structured data that is associated with this corpus, like smoking status and age. Then the next step we do, we create a CMEMS. And CMEM is a minimal unit of semantic meaning. So to map those syntactic values to semantic values, we need those sememes. And we created sememes for cardiovascular symptoms, for family, for such concepts as acute or chronic, and for some possible signs of cardiovascular symptoms. The next step is to search for sentences that contain affirmation of a cardiovascular symptoms. Then we exclude from those sentences those that also refer to family member, because you are not interested in sentences like father has died from infarction. Then we annotate those sentences with semantic values associated with sememes. So we're now already working not in syntactic but in purely semantic space. And now we can recursively apply rules that we developed to those semantic meanings. Well, to summarize this, I would say that if you have to do a work, you should select the right tool for your work. Sometimes you don't have the right tool and you have just to use whatever you have. And well, you probably can extract a nail from your tire using a screwdriver, but if you can select something, you probably should select pliers. If you need to drive a nail in the wall, it's also possible to do with pliers over the screwdriver, but a hammer would work much better. So when you have a project, try to select the tool that is most appropriate for this. Finally, well, there is such tools as a Swiss knife that can be used for every task, but would you really try to do a serious building job using just a Swiss knife? Maybe better to order the proper set of tools. And by the way, I'm not sure that such Swiss knife exists in the area of natural language processing and text analytics. So iknow provides unique and powerful benefits, and thank you very much for listening to my talk. And if you want to know something further, here's some information about to whom you can talk and how to find more information. Thank you. Any questions? Well, I have several examples here. You mean this sentence? Okay. Well, again, remember that CRC is a concept relation concept structure. It's not a triple, really. It doesn't mean that one of the concepts is a subject or object and the relation is a predicate. It's really linguistic meaning. So those are not constituents. Right. No, there's no dictionary of nouns, and that's one of the reasons that it's easier to tune iknow for other languages and sub-languages. There is a linguistic model certainly in place. It's more based on the dictionary of relations, though I don't know how much I should talk about it. No, so yeah. The linguistic model, basically, it first tries to identify relations, and then everything that is not a relation is interpreted as a possible concept, and it might apply some additional logic to actually identify which words in a word group are meaningful to become meaningful concept. Hmm? Okay. Sure. Let me just find this. Yeah. Show the slide with coverage and okay, so that basically means that suppose we need to do some statistical analysis of a corpus of text. A document is a vector in this space where dimensions are, again, single words or I know concepts of noun phrases or something else. We need to select, we need to reduce dimensionality of this space. We cannot have a space with million dimensions because, well, mathematical operations like SVD will require second or third degree of this that will, no hardware can handle it, even your hardware. So here I'm trying first to reduce the dimensionality to maybe a few thousand or better a few hundred dimensions. That means that we need to select the most appropriate set of, say, 1,000 of I know concepts or something. But that concept has to be used, there should be, let's say, at least 20 concepts in each document to do a meaningful analysis, right? Because if there are some documents that do not contain any concept from this set, we can tell nothing about them. So that basically shows, in this particular case, that I think it shows what percentage of the documents of the corpus will have at least 30 concepts from the selected set of a given number of entities, provided we do it in the most efficient way. So it's the best case scenario.